All right, we have three boys, B1, B2, B3, and three girls, G1, G2, G3, at a party. Any boy, let's say B, and any girl G who want to dance together at the party must register in advance as the pair BG. It's possible that a particular pair, BG, of boy and girl, would like to dance more than once, in which case they must register as the pair more than once. So, for example, if they want to dance 4 times at a party for this particular boy and girl, then they must register as BG 4 times. If they want to dance 5 times, then they have to register the pair BG exactly 5 times, so on and so forth. Now, in addition to this, we have the following constraints. First, each boy B can appear in at most 8 of these pairs. Okay? Second, each girl G can appear in at most 7 pairs. And last but not least, each pair BG can have at most 3 dances together. In other words, each pair can register at most 3 times. Here's the problem we want to solve. We want to find the maximum possible number of dances at the party. And to do this, we want to first model the problem as a maximum flow problem in a network. Well, the idea is to think of dances as flow. After all, we want to find the maximum possible number of dances. So in view of a network, that would correspond to the maximum flow in the network. So we're going to think of dances as flow. Let me first model the third condition given by the questions. It says that every pair BG can have at most 3 dances together, which means every pair BG can have at most 3 unit flows in the corresponding network that we want to construct. Well, that means if we have a directed edge, let's say from B to G, if we set the capacity of this edge to be 3, then this forces the pair BG to have at most 3 dances together. You follow me? And therefore we have the following constructions. So if we list down the boys and the girls on the other side with directed edges from the boys to the girls, then if we set the capacity of every such arc going between the boys and the girls to be 3, then we have a network which satisfies the third condition. Okay, so I'm going to put the number 3 here on the directed edges to indicate that the maximum capacity of every such arc is exactly 3. Alright, so this will satisfy the third condition of the question. Next, we're going to introduce the source and the sink of the network. Well, if we let S to be the source and T to be the sink, we'll be able to incorporate the first 2 conditions by having directed edges from the source to the boys with capacity set to 8, since we want each boy to appear in at most 8 pairs. Well, for example, the vertex B1 has capacity 8 from the source, so there are at most 8 unit flow into the vertex B1, and therefore B1 would have at most 8 dancers altogether. Do you follow me? And finally, from the girls to the sink, if we set the capacity to be 7, then this would satisfy the requirement that each girl can appear in at most 7 pairs. All right. So by constructing the following network, we have all the conditions satisfied, and hence the maximum flow in the network will correspond to the maximum number of dances that are possible at the party. All right, so this is the first part of the question. Next, it remains to apply the Ford-Fulkerson algorithm to find such a maximum flow. Okay, we're now ready to apply the algorithm to find a maximum flow in the network. To help keep track of the changes that we're going to make, I have the following table here on the right hand side, where in the first column I have the F incrementing path Q that we found to increase the flow. In the second column, I have the residue capacities on forward arcs on the path Q, followed by the flow on reverse arcs, if any, on the path Q, and the last column is given by epsilon Q, which is the minimum of the numbers we get in the second and the third column. Okay, the initial flow is set to be 0 everywhere. And clearly, there is an F incrementing path given by S, B1, G1, T. And along this path, all the arcs are forward arcs. And the residue capacities are 8, which is 8 minus 0, followed by 3, which is 3 minus 0, and finally we have 7 minus 0. There are no reverse arcs on this path, so epsilon Q, which is the minimum of the second and the third column, is 3, which means we can increase the flow along this path by 3. Okay, let me do this now. I'm going to replace 0 by 3 on this path Q that we have just found. And we have the resulting revised flow. Next, I'm going to find another F incrementing path, where F is the revised flow that we get from the previous step. Okay, an incrementing path that I can find here would be given by, let's say, S, B2, G2, and T. Okay, this is the path in the middle. Again, there are no reverse arcs on this path, and the residue capacities are the same as before. So by revising the flow, we're going to get a revised flow, okay, whose value has been increased by 3 again. Okay, next, there's another F incrementing path which is internally disjoint from the previous two. Namely, this is given by S, B3, G3, T. And the residue capacities are the same as before. Okay? So we can increase the flow by 3 again. Alright, next we're going to find another F incrementing path. So this time, I can choose the path, let's say, given by S, B2, going to G1 next, and then to the sink T. Okay? So again, all the arcs are forward arcs on the path. The residue capacities. Okay, this time, the current flow from S to B2 is 3, and therefore the residue capacity is 8 minus 3, which is 5. You follow me? The arc from B2 to G1 has 0 flow, so the residue capacity is just 3, right? It's 3 minus 0. And finally, for the arc from G1 to T, the residue capacity is 7 minus 3, which is 4. Okay? The minimum of this is 3 again, and we are able to, and therefore we can increase the flow by additional 3 units. This means if I increase the first arc, well, the flow along the first arc by 3, the flow now will become 6, and the flow along the second path, well, the second arc will be 3, and along the last arc, the flow will be 6. Okay? Right. Let's see how we can increase this further. Well, a similar path can be found. This will be given by, let's say, the path as B3, G2, and T. Okay, again, there are no reverse arcs, and the residue capacity along the first arc is 5, as before. The second one, well, the second arc has capacity, well, residue capacity 3, followed by 4 again. And we can increase the flow by 3 as before. So we're going to replace this 3 by 6, and then along the arc from B3 to G2, okay, the flow now is revised to 3, and finally on the last arc, the flow now is 6. Okay. Alright, there's another one on the path S B1 G3T. Okay, and the residue capacities are the same as before. So which means we can increase the flow further by 3. Okay, let me replace this 3 now by 6 after an increment of 3. The arc from B1 to G3. So this flow here will be revised to 3, and finally this one here will be revised to 6. Looks like I'm running out of space here. Let me erase this and continue finding incrementing paths, if any. Okay, there's another incrementing path given by as B1 G2T. All the arcs again are forward arcs. So the residue capacities are 8 minus 6, which is 2, followed by the flow, well, the arc from B1 to G2, whose residue capacity is 3, and the last one will have residue capacity 7 minus 6, which is 1. There's no reverse arcs, and therefore epsilon Q is 1. And we can increase the flow by 1. Okay, let me revise the flow here. 6 will be replaced by 7, and the 0 will be replaced by 1, and the last 6 here will be revised to 7. Okay? Alright, there's another incrementing path, similar to the previous one. This time we have S, followed by B2, and G3, and T. Okay? The residue capacities are 8 minus 6, which is 2, 3 minus 0, which is 3, and 7 minus 6, which is 1. Okay, which is the same as before. So Again, we can increase the flow by 1. Okay, let me revise the flow in the diagram. The 6 here will be replaced by 7, and the 0 here will be replaced by 1, and the 6 here will be replaced by 7. Okay, and finally there's another path which we can use to increase the flow. It's given by the path S, B3, G1, T. Again, all the arcs are forward arcs, so the residue capacities are 2, 3, 1 again as before. So if we revise the flow by increasing 1 unit, the first flow will be revised to 7, and the 0 here will be replaced by 1, and finally the 6 will be replaced by 7. The algorithm terminates here because all the arcs going into the sink T have been saturated. You see, because all the arcs have capacity 7 and the flows are also 7. And hence, that could be the maximum possible number of flows into the sink. Alright? Okay guys, the max flow in this network is 7 plus 7 plus 7. So there will be a maximum of 21 dances at the party. Well, do we know how to list down all the 21 dances? Yes, we do, by looking at the flows between the boys and the girls. For example, B1 will be paired with G1 exactly 3 times because we have flow equal to 3 on the arc from B1 to G1. So this is 3 times. And also we have 1 unit flow from B1 to G2. So B1, G2 will be paired once. And also we have 3 unit flow from B1 to G3. So B1, G3 will be listed 3 times. So on and so forth. Okay, for example, for B2, it is paired with G1 3 times. And then for B1 and G2, we have also 3 unit flow. So this is listed 3 times as well. Sorry, this should be 2. And another pair for B2 will be B2 and G3, which will be listed once, right? Because the unit flow, well, the flow is 1 over there. And finally, for the boy B3, we have a flow of 3 from B3 to G2, a flow of 3 from B3 to G3, and a flow of 1 from B3 to G1, right? So this is listed once, and all the other pairs are listed 3 times. And this is a set of pairs for the maximum 21 dances possible at the party.